Welcome back. In the last class, we looked at radical extensions as well as the notion of being solvable by radicals. Okay, so a simple radical extension is one where it is generated by a single element which is a radical, namely it is an nth root of an element of the base field. A radical extension is one where it is where there are lots of simple radical extensions in the middle. The entire extension may or may not be a simple radical. Okay, and then we say that a particular element is solvable by radicals or simply solvable if it is inside a radical extension, and the extension itself is solvable if every element is solvable. Okay, and a polynomial is solvable if its roots are solvable. So, we looked at examples of simple radical extensions. Kummer cyclotomic extensions are simple radical, and we also looked at examples which are radical but not simple radical. Okay, so q root 2 root 3 as well as splitting field of a polynomial with 3 real roots. Okay, so now our goal today is to prove the following theorem, that splitting fields of cubic polynomials are in fact radical, need not be simple radical, but they are radical. So, the theorem that I want to prove today is, let K over F be a Galois extension of degree 6, okay, of degree 6, then K over F is solvable. That means K is solvable over, that is every element of K is solvable over F. Okay, that is our goal, and I am going to assume characteristic is 0 just to avoid some maybe complications in some specific examples. Okay, so in order to prove this theorem, I am going to prove a very crucial result that will be essential for everything that we do in the rest of the course. So, this I am going to call a proposition. This will be crucial for us. Let K over F be a cyclic extension. Remember, that means K over F is Galois and the Galois group is cyclic. A cyclic extension is a Galois extension whose Galois group is cyclic. Let alpha be, so in L, where L is an extension of K. L is completely irrelevant for us, but all I am really using L for is to get hold of an element which is in L. So, L need not be, alpha need not be in K. So, L is irrelevant except to provide us this element alpha. So, then the statement is K alpha over F alpha is also a cyclic extension, and moreover the extension degree of K alpha over F alpha divides the extension degree of K over F. Okay. So, what we have is, the picture is, I will draw it better. So, you have maybe here L is some big field containing K, there is an element alpha. So, you adjoin that to K and alpha. So, this is cyclic, implies this is cyclic, and the degree here divides the degree here. It can very well be smaller, but it divides it. Okay. The proof is fairly simple, and it is crucial for all our arguments that follow. So, first let us take the Galois group of the original extension to be G. Okay. So, I will first show that K alpha over F alpha is Galois, because remember, a cyclic extension is a Galois extension whose Galois group is cyclic. So, I will first show that it is Galois, then we will show that its Galois group is cyclic. So, by one of the characterizations of Galois extensions, we know that K is the splitting field of a separable polynomial. Right? Separability comes for free because we are in characteristic 0, but the crucial thing is it is the splitting field of a polynomial. So, say K is F alpha 1, alpha 2, alpha r, where alpha I are roots of f. Okay, so this is a trivial statement, by the way. The whole proposition is easy, and this is even easier. So why is this Galois, k alpha or f alpha? So then k alpha can be obviously written as f alpha adjoined alpha 1 through alpha r, and f of course is in fx, which is a subring of f alpha x. So k alpha is a splitting field of a separable polynomial over f alpha, right? It is generated by the roots of the same polynomial, right? So it is Galois. Simple, right? So the same polynomial in capital Fx whose splitting field is k will serve the role for us, will do the job for us, because k alpha is a splitting field of the same polynomial. Now you just change the base field and the polynomial is in the base field, so there is no problem. So this is Galois, and by the way, I don't think I need characteristic 0 here. So separability is an assumption, but we are working with the same polynomial, so that is separable. Second statement is Galois k alpha over f alpha is isomorphic to a subgroup of Galois k over f. So this proves both statements that Galois k alpha over f alpha is cyclic, and this divides this, because this order is k alpha colon f alpha, this order is k colon f. Okay. So why is this? This is because of the following reason. So let sigma be in the Galois group of k alpha over f alpha. So in particular, sigma alpha is alpha, right? So we restrict to k. So this means sigma restricted to k is a function from k to k because k over f is normal, right? So a priori sigma is a function from k alpha to k alpha, which fixes f alpha and it fixes alpha, and then you fix k in this. So sigma restricted to k a priori will land in k alpha, but because k is normal, its image is again in k, so it is an automorphism. So sigma restricted to k is an automorphism of k over f. Of course sigma restricted to f is identity, right? Because sigma restricted to f alpha is identity. Okay. So now we get a group homomorphism from Galois k alpha over f alpha to Galois k over kf, sending sigma to sigma restricted to k. Okay. This is the function. So you take an automorphism of k alpha, you restrict it to k. So phi is certainly a group homomorphism, because you check this, because phi of C circle tau is sigma, phi of sigma circle tau is sigma circle k, sigma restricted to k, circle tau restricted to k, but restriction map is really the same thing. You are just taking elements from k. So this is a group homomorphism, is easy exercise. It's also easy to show that it is 1 1, because suppose sigma k is identity, sigma restricted to k is identity. We also know that sigma alpha is alpha. So that means sigma is identity on entire k alpha, right? Because it fixes alpha by definition, because it is an automorphism of k alpha which fixes f alpha. So it means it fixes alpha. On the other hand, if image of phi is identity, that means sigma restricted to k is identity. So now what are elements of k alpha? They are polynomials in alpha with coefficients in k. Every coefficient is fixed because of this. Alpha itself is fixed. So sigma is identity. So sigma is an injective group homomorphism from Galois k alpha over f alpha to Galois k over f. That means this is a subgroup of this. This is cyclic by hypothesis. So, this must be cyclic. Subgroup of a cyclic group is cyclic. Strictly speaking, this is isomorphic to a subgroup of this. This is cyclic, so this is cyclic. Not only that, because this is isomorphic to a subgroup of this, order of the Galois group of K alpha or F alpha divides the order of Galois group of K over F, but order of Galois K alpha over F alpha divides order of Galois K over F, but this is K alpha colon F alpha and this is K colon F, because both are Galois extensions. Okay? So, this is done. So, this proves this. This is a useful statement that we will use all the time in the rest of the course. And I also want to remark finally about this proposition. Phi need not be in general onto. For example, you can take alpha to be in F, alpha to be in K. Okay. So, if you take alpha to be in K, K alpha is equal to K, but F alpha could be strictly bigger. So, this will be smaller than this. Okay. So, all we know is that this is a subgroup of that. Now, we will come back to the theorem that I started with. Proof of the theorem that I stated at the beginning of this class. So, if you have a Galois extension of degree 6, sorry, K colon F here. If you have a Galois extension of degree 6, I want to show that it is solvable. Okay. So, what do I do? So, K over F is degree 6 extension. Let us take the Galois group to be G, and we know because the given extension is Galois, we have degree 6, order of G is 6. Okay. So, let us take the following. So, what we have is, we know this is irrelevant, but what we know is that G is either Z mod 6Z or G is S6, S3, because those are the only two groups up to isomorphism which have order 6. In either case, what I said is this, it is irrelevant which one it is. In either case, G has a normal subgroup of order 3. In the case of the cyclic group, it is abelian, so every group is normal. So, you take an order 3 subgroup, cyclic group. In S3 also there is an order 3 subgroups generated by 3 cycles, for example, generated by the 3 cycle. So, there is an order 3 subgroup H. Then H is normal in G, since it is a index 2 subgroup. I mean, you do not need the general result, you can make do with the specific statement that in the case of Z mod 6Z, every group is abelian, subgroup is abelian. In the case of S3, the order 3 subgroup is abelian, one can check directly. So, now we apply main theorem. So, we have K, K power H and F. So, main theorem of Galois theory, I mean. So, we have this, and what are the degrees of this? So, let us call this L. Because the order of the group is 3, that is 3, because the index of the group is 2, this is 2. Okay. So, now in this I am going to assume that characteristic is different from 2. Okay. As I said, our primary case is characteristic is 0, but some of these results are generally true. So, we know K L over F is simple radical. This is simple radical because it is degree 2 and F has characteristic different from 2. Any degree 2 extension of a field which is of characteristic different from 2 is simple radical. It is obtained by a degree adding a square root. But now what about K over L? Okay, so we will analyze K over L here. We know that K over L is Galois. This is the usual statement. It is a trivial statement. If K over F is Galois, K over L will be Galois. If for any intermediate field with Galois group, because the only group of order 3 is the cyclic group of order 3. So, Galois group of K over L is Z mod 3Z. So, now this is the tricky thing. This is important. So, what we do now is important. So, pay close attention to this, because we use this idea essentially to prove our next theorem. So, this is a simple example of what I want to do in the general theorem that I will do next. If we knew K over L is a Kummer extension, then K over L is a radical extension, and we are done, right? If it was a Kummer extension, we know that it will be generated by a radical over L. So, but what stops it from being a Kummer extension? But for K over L to be a Kummer extension, it is a degree 3 extension. So, for it to be a Kummer extension, L must contain a primitive third root of unity, right? But in general it may not. See, we are working with an arbitrary field extension K over F. So, and we constructed L along the way. So, there is absolutely no reason to think that L will contain a cube root of unity. And if it does not, as our examples earlier show, if you think about this example, the reason that this fails to be a simple radical is because Q does not contain a primitive fourth root of unity. So, here if L does not contain a primitive third root of unity, we are in a problem, because we are faced with a problem, because then it will not be simple radical. However, remember our goal is to not show that this is simple radical. Our goal is to show that K over F is solvable. So, we are allowed to deviate from the given tower. We overcome this problem as follows. So, let us denote omega be a primitive third root of unity in an extension of K. Okay. So, again let me draw the picture here. We have L, F, this is degree 2, this is degree 3, and we have some large extension M if you want, that contains omega. Okay. This M is irrelevant. All I need to know is that there is a big enough extension that contains a primitive third root of unity. So, as I can see here, I want characteristic of F to be different from 3 also, okay, in order to talk about primitive third roots of unity. So, this I think will hold in all other characteristics. So, we will assume characteristic of F is different from 2 and different from 3. So, we do have an extension which contains a cube root of 3. Now, I adjoin that to omega k omega, and same I adjoin to this. Okay. Now, so we do know that K over L is Galois. In fact, K over L is Galois with cyclic Galois group. So, K over L is cyclic, because K over L is Galois with Galois group Z mod 3Z. So, it is cyclic. Now, this is the important thing. So, this is by the proposition. Proposition says that if you have a cyclic extension, you attach an element to the bigger field and the same element to the smaller field, what you get is a cyclic extension. So, this is a cyclic extension, and now L omega does contain primitive third root of unity by the very construction. So k omega L omega is cyclic and L omega contains omega. This implies, go back to the videos where we did Kummer extension, this says that k omega over L omega is a simple radical extension. Okay, so in that theorem we did not necessarily use the word simple radical, but we did say that it is generated by a single element such that a power of that is in L omega. Okay, so maybe I will quickly show this to you. So I don't remember how long ago it was. So this is a Kummer extension. So okay, so maybe this is good. So F is a field containing a primitive nth root of unity, and K over F is an extension of degree n. Then the following are equivalent. K over F is a cyclic extension. Apply this. So apply this to. So I'll write this for now, but erase this. In our situation, apply this to k omega over f omega. That's a cyclic extension by the proposition. The base field does contain a primitive nth root of unity. So k over f, in this case k omega over f omega, is a Kummer extension. That means there is an A such that k omega is the splitting field of x power n A. That means k is f adjoint nth root of A, right? So we are done. So this is the result that we will apply to conclude that this is a simple radical extension. Now k over L is not in general simple radical, but this is. So this is simple radical. Now we are done. So now consider the following. So I am going to write it horizontally so that it is, I save some space here. So I have f over L, L contained in L omega contained in k omega. Now each of these extensions is simple radical, I claim. This is degree 2, so simple radical. This is simple radical because omega power 3 is in L, right? It is generated by a nth root of unity. So this is a cyclotomic extension. So it is simple radical, and this is simple radical by the argument that I just gave you. Okay. So this is simple radical. So now, and we note now that k is contained in this. So that means every element of k, okay, so basically that means k omega over k f is a radical extension, right? Because k omega, remember, we are not saying that k over f is a radical extension. This is an important point. We are only saying that it is a solvable extension. So k omega over f is a radical extension because there is a tower of simple radical extensions ending with k omega. But k is contained in a radical extension, right? So every element of k, so hence every element of k is solvable over f, because every element of k is in a solvable extension of f, is in a radical extension of f. So let me show the definition I gave in the last class. So an element is solvable if it is contained in a radical extension, correct? So here every element of k is contained in k omega, which is a radical extension of f. So every element of k is solvable over f, and hence so is k. So this completes the proof of the theorem which we started with today, that k over f is a Galois extension of degree 6. That means k over f is solvable. I may have so I can see that this is wrong. it is not necessarily radical, it is solvable. Okay. So, it need not be radical in general, however, it is solvable as we showed here. Okay. So, this idea that we can extend our, so this is a crucial step to go from a given extension with cyclic Galois group, Galois extension with cyclic Galois group to something like this by adjoining any roots of unity that we require, we do get a simple radical extension. So, using this idea, we are going to show later that we can prove that radical extensions are essentially cyclic extensions. Okay. So, let me end this video by a more general stating a more general result that comes out essentially from the same proof is the following. Let K over F be a cyclic extension, then K over F is solvable. What is the proof? The proof is very simple. So, and assume here that important that assume characteristic is 0, because I can generalize this by saying that characteristic does not divide the degree, but I do not want to get into such technicalities. So, assume characteristic is 0. So, the same picture. So, let us say n equal to the degree of this extension. So, let zeta be a primitive nth root of unity in an extension field of K. So, then we have some L containing K containing F, zeta is here, then I take K zeta F zeta. L will go away now, L is only required to construct a nth root of unity. So, this is cyclic by assumption. So, K over F cyclic by the proposition I proved in today's class, K zeta over F zeta is cyclic also, and the base contains a primitive nth root of unity. So, this is simple radical. Okay. So, the tower of simple radical extensions that we consider now is F adjoined F zeta contained in K zeta. So, this is a cyclotomic extension, implies simple radical. This is simple radical because it is Kummer, and K is contained in this. Okay. So, every element of K is contained in a radical extension. So, this basically implies that K zeta over F is radical. So, every cyclic extension is solvable. This is something that we will use essentially. This is the crucial idea in the proof of the next theorem. But let me stop this class here today. In the next class, we will discuss more properties of radical extensions. Thank you.